Hi there, Year 8, and welcome to this lesson on the speed of sound. So I wonder if any of you can tell me what the relationship between thunder and lightning is.
Okay, so I'm all wrapped up warm because I'm going to go outside and measure the speed of sound. What we're going to do is we're going to go to a little field near our house, and my cameraman is going to be 100 metres away from me, which is the length of the field according to Google Maps, which is great. I don't have a trundle wheel at home, so I can't measure it, so I Google mapped it. And what's going to happen is I'm going to shout a word, and as soon as hello, and as soon as my son who's filming hears it, he's going to put his hand up. I'm going to have a stopwatch. I'm going to start it when I say hello, stop it when he puts his hand up, and I'm going to write down the time. Now, to do this accurately, I'm going to repeat it. So we're going to do it 5 times, and we're going to see what results we get. It's going to be really cold, so we're going to do it as quickly as possible. All right, let's go to the field.
Okay,
Have you pressed the red button?
Yeah.
Excellent. Okay, so what I'd ideally like for all my lovely Year 8 students to do, watch where your hands are, darling. So all my lovely Year 8 students, what I would like you to do is ideally find somewhere where you can have 100 metre distance, which is plenty social distanced, and maybe you and a friend can do this, do a sort of a shout and a time, and have the other one record it. So a few questions. I need you to pause the video. Not you, darling. Okay, sorry, I've got my middle son filming at the moment, so that's why it's a little bit wobbly. What I'd like you to do in a moment is pause the video and just write down a few things. So I'd like you to write down why we're doing 100 metres and not 10 metres. Why is 10 metres too short? A kilometre would be better, but why might a kilometre be a little bit too long? So why did we do 100 metres? And I want you to write down why we might not be getting an accurate speed of sound in air, because this isn't going to be perfect. And I want you to say, well, why not? Why would this be less than perfect? What on earth has Mrs. Smith done wrong in an experiment that it's less than perfect? So that's what I want you to do. I want you to write down what the problems are, write down why 100 metres and not 10 or metres or a kilometre. And if you can, I want you to go out and I want you to do the experiment yourselves and see what data you get. Okay, so I've got my little dinosaur notebook here, and in it I've measured all the times. Okay, so hopefully you can see all my measurements here. My distance was 100 metres. But was it? I mean, I measured it on Google Maps. We stood in the right places, but was it exactly 100 metres? So that could be one cause for error already. And here's my time. And we did it 6 times in the end, because look at that one. That's about twice the length of some of these. So this one has to be an anomaly, and I'm going to circle it. How exciting. Here's a little tip for you guys, okay? When you are doing any tests or exams and you're asked to calculate an average, always look for a little odd man out like this one that doesn't fit in with the rest of the numbers. That's called an anomaly. Okay, and I've just written anomaly down there for you. And we ignore it when calculating our mean average. Okay, so what was the average time?
I'm going to get my big calculator here and I'm going to put the numbers in. 1.65 seconds plus 1.04 seconds plus 1.05 seconds plus 1.33 seconds plus 1.28 seconds. Okay, and that gives me 6.35. I then need to divide that by the number of figures I put in. And remember, I put in 5. I did 6 measurements, but that one was a lovely anomaly. So I'm going to divide it by 5 because I've ignored my anomaly. And I get 1.27 for my time. So my mean time is 1.27 seconds. Okay. So here's another question. Why do you think the first one was an anomaly? Why was the first one quite far out? As you can see, I didn't reset my stopwatch for the second one, so I had to do second time minus the first time to get the actual time. But why was that one an anomaly? And why would we expect the first one to possibly be an anomaly? Okay, so write that down, please. I do want to see all of this that I've asked you to write down. So I do want to see all of this emailed to me. Next thing to do, calculate speed. And if you remember, speed is measured in meters per second, which is meters divided by seconds. Okay, so we do distance divided by time, meters divided by seconds. Our units tell us that. So let's go back to our calculator. We've got 1.27 seconds, but we need to do 100 meters divided by 1.27 seconds. And we get 78.74 meters per second. So let's pop that down. 78.74 meters per second. So I think that's what the speed of sound is. But is that the speed of sound? Well, no. Sorry, I've just noticed you're upside down. That is not the speed of sound. 78.74 is not the speed of sound. The actual speed of sound is about 330 meters per second in air. This would mean my timings should have been about 0.3, 0.31 maybe, but 0.3 seconds long. That's not really viable, is it? I'm not going to get that sort of result. So what we need to do now is we need to think of ways to improve this experiment. So we said before that 1 kilometre wasn't a good idea, and you've already told me why. Okay, so just think about how big the field size is near you and how far you can hear a sound. Think about as well, if we wanted to do it over a kilometre, so then we'd have about 3.03 seconds for our speeds. If we did want to do it over a kilometre, how could we make ourselves heard? And this would be a lovely opportunity for you to go off and look into things like yodeling and other ways of being heard over long distances. So I know that the First Nation Australians, for example, did a coo-ee sound. Not quite, ooh, coo-ee, over the garden fence to catch a neighbour, but a proper coo-ee can travel a very long way. So yeah, but finding the space, finding somewhere that is a kilometre long that you can see each other at either end and hear each other is a little bit difficult. I could have easily made this 200 metres though. How could I have made my distance 200 metres when I was stood in a little patch of field that was 100 metres long? Well, what we could have done, okay, so you're going to, sorry, I'm filming this myself at the moment. So what we had, you're being treated to my awesome drawing skills again. What we had was me in my little hat over here shouting
distance of 100 metres, and my son here sticking his hand up when he heard me. What could have happened though is I could have shouted, the sound could have travelled to my son and he could have shouted in return, and when that sound returned to me, then I could have stopped the stopwatch. Oh, sorry, I've just realised you were tilted again. So I could have stopped the stopwatch after it had gone to my son and back again. There are problems with that as well, though, obviously, because then you're also taking into account he's got to hear and shout, and then I've got to hear and stop, and it's human processing time that's the problem. Let's be honest here. There's a little bit of speed of light as well that we're measuring, because I'm measuring how long it takes me to see that my son's raised his hand, but quite frankly, the speed of light is pretty darn fast, so that's not going to make too much of a difference. But the speed of human processing does. Human processing seems to be the problem. I wonder what we could do to solve that then. What could we do? So I want you to write down your answers. Pause the video, have a good old think about it. What could we do to solve the problems? If human processing speed is the problem, what can we do to solve it? Okay, so here's an example of using an echo to measure the speed of sound. Okay, so shouting at a wall 100 metres away. Sorry, that was upside down. Let's sort that out. So you can shout at a wall 100 metres away and have it bounce back. That would take out the human element here. But an easier way to do it is by using a computer. And what we've got here is an ocean an ocean liner, which is measuring the depth of the ocean and where a wreckage is at the bottom of the sea. And it takes a certain amount of time for the signal to get to the wreck, and then the signal goes back up. Okay, so we've got a part of the ship at the front will send out a pulse of sound, usually ultrasound. Ultrasound just means anything above about 20,000 hertz. So anything that's a little bit too high for humans to hear. And it gets sent down and it goes back up. The reason that you're seeing it at an angle is because the ship is moving. So as the ship goes over the wreck, it's sending a pulse down. And as the pulse comes back up, it's picked up at the back of the ship. Okay, it's not going diagonally because then you'll get an incorrect distance. Okay, so it's going down this way. So it goes down and it comes up. And the speed in water is 1,500 meters per second. So speed is a lot faster in water. Sound is a lot faster in water, sorry. So it goes down and comes back up again. But as I say, the ship's moving, which is why it looks like it's at a diagonal. They always do this at a diagonal, and it's not quite correct. It's correct for the parts of the ship. It is not correct for the fact that it's going straight down and coming straight back up again. And the other thing I need to say about this is that because it's going down and coming back, you've got twice the distance. Now, if you're doing it with yourself, that's fine. You know it's 200 meters. But when you are trying to measure the ocean floor, it's a little bit more difficult. Only a small part of the ocean has been mapped so far. So what I'd like you to do is find out how much has been mapped. Find out how much of the ocean floor has been mapped. That's a little research bit for you to do. So you've got double the distance. So you know the speed and you know the time, because in this case it took 1 second, half a second to go down, half a second to come back. And you would have to do the distance is time multiplied by speed. So you'd have to do the time multiplied by the speed to get the distance. But because you've got double distance, you'd have to
halve it. So you'd have to do half the time multiplied by the speed. Okay, so just be aware that when you've got an echo, to calculate the distance, you have to halve it. Right, last question from me, I promise, and then I'm going to let you go and hand some stuff into me. Why is the speed of sound faster in water? Okay, so in air, it's about 330, maybe 340 meters per second. In water, it's actually 1,496. No, sorry, 1,454 meters per second usually. It's just rounded for the sake of convenience to 1,500 there. So why is it so much faster? Why do you think? I'm going to tell you the answer to this one, but pause it and write down why you think it is. It's because there's more particles to hit together. If we remember our particles, our gases are all spaced out and our liquids and solids are close together. So that means that sound can travel through a liquid. It's bumping particles together. So if the particles are closer together, it's easier for it, it's faster for it to move. And as well as which, it can travel further. I couldn't make my voice travel for a mile, but a humpback whale song can travel for up to 100 miles. Okay, that's incredibly far. This is another amazing fact, that the speed of sound is about 35 times faster in diamonds than it is in air. How cool is that? So your diamonds make sound go so much faster. Right, I'm going to have to go now, but you've got loads of questions from my video to answer. They should be in the description down below as well. And hopefully you've been able to do your own experiment, get your own speed of sound. Your reactions may well be quicker than mine, so you might find that your speed of sound is a little bit faster than mine. Anyway, really looking forward to seeing what you hand in, and I will see you again very soon. Take care. Bye.